Math 287, Quest to College. I'm Joe Vasta, and we are going to cover section 8.2, constant coefficient homogeneous linear differential equations. Wow, what a mouthload. So what we have here is we have this differential equation. Wow. And we have to explain what all this stuff is, what it means. The order is the highest derivative. We discussed that in another video. And so the highest derivative is the nth derivative right there. And notice we have y, it's the nth derivative of that, and we have a sub n x. We just call that function, put an n there. Okay, the linear means the yi's are on their own. They're not multiplied by each other. They are all raised to the first power, and they are not arguments of logs, trig functions, etc. Homogeneous means f of x equals 0. F of x is sometimes called the driving function, and we will see some applications in this chapter. Constant coefficients means that the AI's are constants. Okay, so those will be constants. And that's the kind of differential equation that we will be solving in 8.2. I'm going to try something new today. I have some PowerPoint derivations, and we're going to see how bad this can be. So, well, just hang in there and you'll see. You'll see some craziness. So our first differential equation that we're going to solve looks like this. Solve y, like 6y double prime minus y prime minus 15y equals 0. Now, if you look back at the 8.1 lecture, we realized that we can write something called the auxiliary polynomial, which looks like this. 6r squared minus r minus 15 equals 0. And we kind of did the derivation. What function, when you take some derivatives of it, give itself, and it was e to the rx. And that's what we're looking for. We're looking for the r on the e to the rx that will solve this differential equation. So this differential equation comes down to factoring this trinomial. And so I'm going to go ahead and show you something called the big X method for factoring trinomials. Lots of teachers would call this trial and error, guess and check, but there's really no guessing about this. So the first thing I'm going to do is I'm going to go 15 times 6, which gives me 90. Okay, I find factor pairs of 90. 1, 90, 2, 45, 3 times 30. Does 4 go into 90? No, it doesn't. 5 goes into 90. 5 goes into 90, I think 18 times. Let me just check. I'm feeling brain dead today. So, yes, it is 18 times. 6 goes into 90 15 times. So 6 times 15, 7, no, 8, no, 9, and 10. So what I'm going to do is I'm going to find the factor pairs that, let's use a highlighter on this, that subtract to give me 1. Okay, there's a 1 in front of there. I know there's a negative 1, I'm ignoring the negative 1. So these factor pairs here subtract and give me a 1. So that means this thing can be factored. We don't have to do the quadratic formula. I'm going to take factor pairs of the leading coefficient, 1, 6, 2, 3. I'm going to take the factor pairs of the constant, which would be 1, 15, 3, and 5. I'm going to draw a big X, and now I have to multiply across these lines to get 9 and 10. So maybe we should work on the 9. It doesn't matter which one we can work on. So 9, I'm going to have to multiply 2 natural numbers to get 9. So if I'm looking up here, I'm either going to pick the 1 and the 6 or the 2 and the 3. Now, I don't have a 9 over here, And 6 times a natural number is not going to get me 9. So I'm going to go pick the 2 and the 3 because I'm looking at 3 times 3, which would give me the 9. So we've picked this one, and it's actually already determined that I'm going to use the 3 and the 5. So I'm going to put the 5 down there. 2 times 5 is 10. So there was no guessing. We were just using logic to figure out what goes there. Okay, let me go ahead and move my sun blocker. Okay, so what we want to do now is adjust the signs. I need a -1 there, so this 10's got to be negative and this 9's going to be positive. So the 9, 3 times 3, 3 times a positive 3 gives me the positive 9, and 2 times negative 5 gives me a -10. You always have to put the signs on the right side, and there is your answer right there. It says 2x plus 3 and 3x minus 5. But we have r's there, so I'm going to write this as 2r plus 3, and then this is multiplied by 3r minus 5. This equals 0. We're in a differential equations class, and the hardest part about this problem was something from many classes ago, factoring a trinomial with a 6 out front. I set each of those equal to 0, and I get 2 r values. I get r equals -3/2, and the other one gives me r equals 5/3. So let's go ahead and write up the solution to our differential equation. If we remember back from 8.1, this is what we do. We say y equals c1 e raised to the -3/2 x, so -3/2 x, plus c2 e raised to the 5/3 x. And that's our answer. Really what we found is we found the kernel of some linear transformation described by 6d squared minus d minus 15. And so that's what we're doing when we do this. This is a linear combination of 2 vectors. But if you don't want to remember all that linear algebra stuff, just remember that the order is 2 and you have 2 constants. So that is problem number 1. The hard part of the problem was factoring a trinomial. So you'll get that in your homework. Let's go ahead and do problem number 2. Problem number 2 looks like this. Y double prime minus 4y prime plus 4y equals 0. I'm going to jump right to the auxiliary polynomial, and then if I set it equal to 0, that's the auxiliary equation. R squared minus 4r plus 4 equals 0. And then we end up getting, this one's a little easier to factor than the other one, r minus 2 quantity squared equals 0. And what I end up getting on this problem is an r value of 2, but it has multiplicity, or we were calling it algebraic multiplicity 2. So what's going to happen to this? Well, let's go ahead and explore the PowerPoint that describes this. The PowerPoint is going to be a derivation, and you really don't want to write down everything in the PowerPoint. I'll provide it in the notes. So we have this second order homogeneous linear differential equation with constant coefficients. And we write out the auxiliary equation. R squared minus 4r plus 4 equals 0. So we factor that, and we see that r equals 2 with an algebraic multiplicity of 2. Now, we're going to take a guess on what the solution would be to this differential equation, and our guess is going to be we have c1 e to the 2x plus c2 e to the 2x. So that's our guess. Because we have one value of r, but it has algebraic multiplicity too, so why not just do that? Now here's the deal with this expression here. Each of those terms has an e to the 2x, so I'm going to factor that out to the right, and then I'll have a c1 plus c2, which gives me just a constant, c. There's two problems with this. Problem number one, the solution needs two independent vectors. Okay, we do not have two independent vectors. In fact, it's a second order differential equation. It should have two CIs, and you can say, oh, we have two CIs over here, but the vectors e to the 2x and e to the 2x, those are the same vector. Those are not independent vectors. Our second problem with this guess, and it was a good guess, is you could be given those initial conditions, y of 0 equals 1 and y prime of 0 equals 3. And when you crank these values into this solution, I'm not going to go through the details, but you get 3 equals 2, which is a contradiction. So now we're going to take a guess of what the solution can be. Our guess is probably going to have that e to the 2x in it, but it's going to be not just a constant, it's going to be a function of x. So we'll write our guess as y equals u e to the 2x, remembering that u was a function of x. So what are we going to do? We're going to plug our guess into the differential equation. In order to do that, we need y prime and y double prime. So there's y prime. I did the product rule, the derivative of the first times the second, plus the first, which is u, times the derivative of the second, which is a little chain rule, 2e to the 2x. I'm going to go ahead and take the second derivative of this differential equation here. And the second derivative looks like this. So what I did is I did the product rule for derivatives here, and I did the product rule for derivatives there, and then I combined like terms. So there are the first two derivatives of y. I'm going to plug y prime, and y double prime into the original differential equation and see what we get. So you can see how it says y double prime. So this is y double prime right here. And then my differential equation has a minus 4y prime. So here's minus 4, here's y prime. And then plus 4y, which is right there. Now, each of those terms, like if we went ahead and multiplied the -4 through, distributed the -4, all those terms have an e to the 2x, which I'm going to factor out to the left, and I'm going to end up getting that expression within the brackets. But notice this expression within the brackets. I have a 4u prime and a -4u prime, and then the 4u and 4u and -8u, all that goes away, and I end up getting e to the 2x u double prime equals 0. Well, e to the 2x could never equal 0, so that would tell me that u double prime has to equal 0. I'm going to take the antiderivative of both sides of that equation. The antiderivative would give me u prime on the left plus a c, and then on the right I'd get another constant, so I'll just call that c2. So u prime equals c2. I'm going to go ahead and take the antiderivative on both sides of this equation. I'm going to get u on the left, c2x plus another constant, which I'll call c1. Okay, so that is what the function u looks like. Let's take a look at my solution. Remember, my guess said u times e to the 2x, so I'm going to put that over here. U times e to the 2x. The u that I found is c2x plus c1. We can rearrange things with algebra. and I get my final result, which is C1 e to the 2x plus C2 x e to the 2x. So this whole derivation was to show us that if you have algebraic multiplicity 2, it puts a little x right there on that one. So e to the 2x and x e to the 2x are two independent vectors, and that ends this derivation. Back to the problem. So like if you were doing this in your homework, you would go, aha, the algebraic multiplicity is 2. Let's jump right to the solution. Y equals C1 e to the 2x, and that's what you would normally do. I'm kind of writing up what was on the PowerPoint, plus C2. Now what we wanted to write was, maybe e to the 2x, and we found that there were problems with that. So the thing you have to remember is an extra x goes right there. The vectors e to the 2x and x e to the 2x are independent vectors, and they form a basis for the kernel of a linear transformation, but you don't even have to think about that. We are done with this problem. Let's go ahead and do the next problem. Problem number 3. So this one, we have y double prime plus 2y prime plus y equals 0. Let's go ahead and write down the auxiliary equation. R squared plus 2r plus 1 equals 0. I factor this into r plus 1, quantity squared, equals 0. So this gives me r equals -1, which has an algebraic multiplicity of 2. Which means when I write out my general solution, I'm going to write C1 e, I'm going to use my r value, to the -1x, so to the negative x plus C2 x e to the -x, and I'm done with that problem. So when you go to do your homework in 8.2, the hardest part may be, after the memorization, the hardest part would be factoring trinomials. Okay, let's go ahead and do problem number 4. Problem number 4 looks like this. Okay, y double prime minus 6y prime plus 13y equals 0, the auxiliary equation. R squared minus 6r plus 13 equals 0. Factors of 13 that add up to give you 6, that's not going to happen, so I have to use the quadratic formula. Minus b plus or minus the square root of b squared minus 4 times a times c. This is all over 2 times a. So this gives me 6 plus or minus the square root of 36 minus 52 all over 2. This gives me, let's see, 6 plus or minus the square root of -60. Some of you have already fast forwarded through this part. You're like, yeah, I know how to do this. And then this gives me 6 plus or minus 4i all over 2. I can split the fraction and write this as 6 over 2 plus or minus 4i over 2. And this gives me 3 plus or minus 2i. Okay, so we have imaginary numbers, and we're going to find out in the following sections that imaginary numbers are as real numbers. This pops up in differential equations when we encounter oscillations. So we'll get to that. So what do we do? How do we write our solution? Is our solution going to have imaginary numbers in it? And the answer is no. We don't want to have imaginary numbers in our final solution because our final solution might represent the position of a particle or something on a spring or something on a circuit. So we've got to deal with this. So we need another PowerPoint derivation, and that's what we're going to do. So I'm going to go ahead and put the laptop back. Before I talk about this problem, I'm going to do a derivation of something that probably should have been done in second semester calculus. However, some of you may never have seen this. So now we're going to do a derivation of an outstanding formula that is used in math a lot. But before we start doing this derivation, we have powers of I to the 1 is I. I know I to the 1 is also the square root of -1, but we're going to write it like this. I squared is -1, I cubed is -I, and I to the 4th is 1. We're going to need to know that. So let's analyze e to the ix. Well, we do have power series for e to the x, and I'm just going to plug in ix instead of x into my power series, and I end up getting this. Okay, so there's the power series. Some of you might remember that. Okay, well, the next thing that I'm going to do is I'm going to use these guys down here and replace I squared with -1 and I cubed with -I and I to the 4th with 1, and that has this effect. It makes the sequence have plus plus minus minus plus plus minus minus, and really you only see i's in there. You do not see I squared or I to the 7th, and it seems like every other term has an I in it, and then the other terms have no imaginary part. So I'm going to really split that up into two parts here. And so I went ahead and put all the non-I terms right here and all the I terms right there. I'm going to factor out an I on the second part. And so there's the I. We pulled an I out, which is always a cool joke in a math class. And now I just have a regular infinite series without any imaginary numbers there, and then same here. And you might recognize these ones. Here's the even powers, and it alternates in odd powers, and it alternates. You can grab a calculus book if you want to check this out, but those turn into the cosine and the sine. And so e to the ix equals the cosine x plus I sine x. That is an amazing formula, and that is used a lot in the world of math, and it gives us oscillations. So what we want to do, just to make this really neat, is plug in pi for x. So x equals pi. We know that the cosine of pi is -1 and the sine of pi is 0, and this gives us this really neat formula that says e to the pi I equals -1. So let's get back to problem number 4 and see how we can deal with imaginary numbers. So there's a second order differential equation. We'll write up the e to the ix equals cosine x plus I sine x. That's what we derived. We'll also write up those identities. The sine function is odd and the cosine function is even. That's basically what those ones sum up to. The auxiliary equation looks like r squared minus 6r plus 13 equals 0. And using the quadratic formula, we end up getting some r values. R equals 3 plus 2i, and it also equals 3 minus 2i. So we're going to go ahead and plug those into the solution here. So, you know, this looks like a solution, but this solution is not simplified, and it's not going to help us in the real world. We're not going to want to have those imaginary numbers in the exponents because it will cause our CIs to also be imaginary numbers, and it's just going to be a lot of algebra algebra to do problems if we kept things this way. So we're going to consider this not simplified. So both of these terms can be algebraically manipulated, and that's what I'm going to do. We're going to write out, the first term is c1 e to the 3x times e to the 2ix. And then the same thing with the second term. Each of these terms have an e to the 3x in common. I'm going to factor that out. And now I have c1 e to the I 2x. And then this one's plus c2 e to the I negative 2x. Well, I'm going to plug these guys right here. You know, like look at the first one. It says e to the I times 2x. I'm going to plug that into this top formula here. And I'm going to replace x with a 2x. And the same thing with the other one as well. I'm going to replace the x with a negative 2x. So that gives me this expression right here. Now I'm going to use these formulas to kind of get rid of those negatives in those arguments there. And when I use those formulas, I end up getting a negative right there, and then this one's a positive because that's the cosine. The next thing I want to do is I want to group the two terms inside the brackets that have i's. I want to group them together. And then the ones that don't have i's, I'll put them in the front. So that's what I did. And then the next thing I want to do is I want to factor out a sine 2x from both of those terms there, and factor out a cosine 2x from the first two terms. So we have something that looks like this. c1 plus c2 is a constant, so I'm just going to call that another constant. And then, believe it or not, c1i minus c2i is just some constant. And I'm going to replace that with c4. And there is the result. We have e to the 3x. The 3 comes from the first part. And then over here we have constant cosine 2x plus constant sine 2x. The 2's come from right here. And so instead of doing this every single time we get imaginary numbers for our R values, we can just remember the formula and it will be a lot faster. We've done memorization of formulas in the past, like with derivatives. We don't go back to the definition of the derivative with the difference quotient to do that, and same thing with this. So now we'll go back to the paper. Now I know we know what the answer is, but let's kind of analyze what we have to memorize. When I get 3 plus or minus 2i, I'm going to go like this. I'm going to say that y equals, now solving this differential equation, is going to be e, and then I use this 3 right here, 3x. And then in here, I could put parentheses there if you want. Then I'm going to use the 2 because that's going to tell me what goes in the cosine. So this is going to be c1 cosine, so there's the 2, 2x plus c2 sine 2x. And that completes my problem. Lots of books will write it this way. Some of you might want to write it like this and just have it so it says c1 e to the 3x, because that kind of reminds you of the other problems. And then we have the cosine 2x plus c2 e to the 3x sine 2x. So some of you would like to write your answer like that. It doesn't matter which way you write your answer. So that pretty much gives us all the things that can happen to you in your homework. And so let's just kind of sum it all up with this piece of paper right here. Second order, so we're just looking at second order because that's all we've done so far. Constant coefficient homogeneous differential equations. They'll always have auxiliary polynomials that are second degree, which means you can always use the quadratic formula to get the 2 roots or 2 zeros. And so let's summarize all the stuff that can happen to you. The 3 things that can happen would be these 3 things right here. Now, notice the quadratic formula has something called the discriminant, and you know, we saw that right here. So let's take a look at that. And if this discriminant is negative, you end up getting, you know, two imaginary numbers. If this discriminant is positive, you end up getting two real numbers. And in fact, we didn't use the quadratic formula on problems 1 or 2, but we could have. And the discriminant, this thing right here, would have been a positive number, and that we could have got the same answers. The other time is when this yellow part is 0, in which you only get one answer. And I think what happened is that happened on problem, that happened when we had the repeated root. You know, when you have like r minus 2 quantity squared, that would have been 0. So let's take a look at all the things. Those are the three things that can happen. You know, that's when the discriminant is 0, that's when it's positive, and that's when it's negative. And let's just kind of, we know this, but this is something we want to memorize. So this is the one we just did. Your solution to the differential equation will look like this. E to the ax, so we take the real part for that. And then we have C1 cosine bx plus C2 sine bx. Now when you have two distinct real numbers here, your solution, this is the first one we looked at, C1 e to the ax plus C2 e to the bx. And then the last one is when you have a repeated root, which is C1 e to the ax, so the repeated root is a, plus C2, don't forget your extra x, e to the ax. So this summarizes everything we've done so far. And that works for all second order constant coefficient homogeneous differential equations. Let's go ahead and take a look at something that is more than second order. First of all, maybe you can figure out which order this is. Okay, so if you're having a hard time, this is written in the operator notation. The order is, there's a d to the first here and a d third there and a d to the fourth there. The order is 8. Because that would happen to be the degree of that polynomial if you're not looking at the y. So you might think to yourself, well, what should we do? Should we multiply this all out? Absolutely not. We do not want to multiply that all out. We want to write the auxiliary equation, and when it's written like this with the operator notation, the auxiliary equation is just going to be this part with the d's, but the d's will be r's. So watch this. This will be like r minus 7, r minus 4 cubed, and then here we have r squared minus 2r plus 3 squared. This equals 0. Okay, so that is one of the sweet things about solving constant coefficient homogeneous differential equations. It's not so sweet saying it, but maybe it is. I don't know. Let's go ahead and find our solutions. We have 7, which has, we'll just say multiplicity. I know we've been calling it algebraic multiplicity, but we're not doing eigenvalues and eigenvectors at this moment. Then we have 4, which has multiplicity 3, and some of you might wonder, maybe you want to stop this and see if you can write out the actual solution. This one is a quadratic formula, so I'm going to save you the details, and what I ended up getting 1 plus or minus I root 2. Now, some purist would have put the root 2 first and the I after the root 2, but sometimes, you know, the I wants to go into the house, especially if it's raining out there. So these have multiplicity 2. I'll just say each. Okay, so they each have multiplicity 2. Let's go ahead and write out our solution and see what happens. So right here we have the case two imaginary numbers. we have multiplicity 2, and then we have a repeated root, and then one that's not repeated. Let's write the solution. There are going to be how many constants, or how many CIs? There will be 8. So here it goes. Y equals C1. Okay, we're going to start off with this one. We'll go from left to right. It's going to be e to the 7x plus. Okay, so we're done with this one. Check. Now we have to go C2 e to the 4x. So we're not done, because this is going to give us 3 constants. And, you know, we've done one that had multiplicity 2, so let's just go ahead and write out what we think it's going to be. This is going to be C3x e to the 4x. And so now we need one more from this. Okay, and the one more from this is going to be C4, and maybe your guess is as good as mine, x squared e to the 4x. Okay, so that takes care of those guys right there. Or shall I put 3 check marks there? Okay, so that takes care of 4 of the CIs. Now we're moving over here, which is scary territory. The real part is 1. The imaginary part, you know, what we call b, is going to be root 2. So let's see if we can do this. So it's going to be plus, I have to continue it down here, e to the 1x, and then we have C5 cosine of root 2x. I'm going to write it like x root 2 for the same reason, the x. Sometimes mine tries to sneak under the square root. So it's just problems that I have. You can put the x after if it's not under the square root. Plus C6 sine x root 2. Okay, so because these each have multiplicity 2, we're going to kind of play the same game that we did here. We're going to go e to the x, and perhaps we should have put the x in front of it. It doesn't matter which order you put those in. And then we go ahead and write out this again, making sure that we don't say C5 and C6, but maybe C7 and C8. So C7 cosine x root 2 plus C8 sine x root 2. So this is the first 8th order differential equation that we've ever solved. And that's kind of neat. So we're able to solve really cool differential equations. Okay, we're done with this section. Let me just go ahead and show you something that, you know, sometimes people do on exams. They see something like this and they're like, oh, I want to solve this. And so they'll go like this. So I'll write it in red, and maybe you can wonder why I'm writing it in red. The auxiliary polynomial is going to be r plus 2x to the 4th equals 0. So the reason we cannot do that is because this guy right here is not constant coefficient. So this thing with the auxiliary polynomial can only be done for constant coefficient differential equations. Now this is first order, so you can bring this to the right hand side and use separable variables, or you can notice that it's linear. There's other ways of doing this. But on the test, sometimes I see people's auxiliary polynomials, they have r's in them, but they also have x's, which means they weren't careful. Now if that x to the 4th wasn't there, and it said y prime equals 2, y prime plus 2y equals 0, sure, it's separable, but you could now use the methods that we learned and get an answer probably faster than you can do separation. So that is really where we're going to end this. In the PDFs, I'll also include the big X factoring technique And I'll just kind of tack it at the end, so when you're looking through the PDFs, you have to go to the last few PDFs to see the technique. Well, that completes 8.2. You guys have a good day. Goodbye.